So today my topic is mostly focused on the seismic application, how we can use the steel for more earthquake resistant applications rather than the conventional gravity load design system. In this lecture, I will briefly go through the type of the system we can design with a focus of like earthquake resistant structures, and then how we can further utilize the steel in concrete structures also for retrofitting applications. I see that a lot of a lot of discussion has been going on, like how to utilize the steel, what are the advantages, disadvantages, all these things. I have some slides on this. I will try to skip those slides. So essentially, like we have different kind of structural systems, starting from the residential buildings, towers, like high-rise, low-rise, industrial structures, even the bridges, stadiums, where we mostly use either concrete and steel structures. In India, the concrete structures are more popular, probably like one of the basic the cause or the reason for this is we always look at the material cost and probably like which material is easily available to us. So that is why like we have, usually we are going by the traditional way of using the concrete and masonry structures. The steel structures is getting popular, and it's not that like, what Mr. Bedi was asking, whether we need to change our curriculum. I think every, university has a course on the steel structures. The probably like the way we perceive which are the more prevalent construction, people go in that way. So we need to actually look at like how to utilize the steel, be it at the manufacturing level, be it at the consultant level, be it at the client information, like the client should be more aware of the like what are the benefits of steel and the concrete. Coming to this, I will just keep this slide because many of the, mostly all the presentation have all these advantages of the steel and disadvantages. Mostly I will focus on like one aspect is your seismic resistance properties, and there are three limitations, which is the corrosion, low fire resistance, and you have slender sections, which is in the structurally we call like it can buckle. And how to actually even utilize this aspect in a positive way in earthquake resistance design. Not the corrosion part, obviously, but the last part, like taking the buckling into account. So we have different kind of systems, like mostly like eyes, channel section, angle sections, and so utilizing this actually like it's a new term, probably like some of you have heard of this. This is called the die-grid structure. Die-grid structure means like everything is on your perimeters, and this building is an example of the die-grid structure. So which is in the South Australia, it's a hospital building. If you see this building actually looks like the outer, it's a skin of a pine cone. And if you go to the very detail, you will see that like the outer shell consists of some kind of cold form hollow structures. What are the advantages of this is, if you see this probably is not clear, it actually reduces around 50 columns at the ground floor level. So it gives you the better space, workable space. This is just one example I'm trying to show this. And it also gives you the better architectural effects. And it has a better load resistance capacity. I'm not talking about the earthquake point of view, but not all the area of any country is earthquake prone. Sometimes you probably don't need to consider the earthquake if it is not falling under the some kind of seismic high seismic zones. So the essence of this structure is like, this is just one example, like you can have a very beautiful structure using the steel and arranging in different in different configurations. Now when you have the earthquake applications, so so we define, we called as like, any system which carry the earthquake is called the lateral load resisting system. I'll briefly go through this, how we arrange the steel in different lateral load resisting system. You can just layman a point of view, one can think of a specific system in this structure, not all the beam and column are designed to resist the earthquake load. Since the earthquake load is like you don't expect at any time, but you have the gravity load at all the time. So all the beams and columns in this structure are not designed to resist the earthquake load. So they are active, and whenever there is so they will be active whenever there is earthquake, and mostly they carry your gravity load, or you can say inactive when there is no earthquake load. So look, does not mean that in RC building we by default we do the detail or design each and every beam and column to resist the earthquake force. In the steel design, there is a basic difference. You do not need to design your beam and column to resist the earthquake force. You can separate the entire beam and column. Out of, let's say, 200 columns, probably 10 columns will take the earthquake force, or remaining 190 columns can be designed only for the gravity force. So seismically, like what it gives you, it gives a better utilization of the material, more cost-effective way. So one of the best example of the seismic resisting system is called as the moment resisting system, which is essentially nothing but like you have a vertical member called as the column and the horizontal member called as the beams. Now, the beauty of this, like if you compare the steel frame versus a concrete frame, your concrete frame, if you keep the all other parameters, loading and everything constant, your concrete building is more stiffer as compared to the steel. So the more stiffer means it attracts more earthquake force. So on the other side, your steel building is flexible. That means it resists lesser force, but at the same time, you have a little bit higher deformation. But if you would control the deformation within the limit, you know that if you are sitting on a slab, you have a beam supporting the slab, you have some kind of deflection. It doesn't mean that you don't have the deflection, but that deflection you say is okay when it is within the limit. So that if you design the same thing here, it's just the combination of beam and column. And if you design, and it can be well designed, because steel is I think is one of the few material where you can utilize their stress and behavior in a more confident way, where you have more probability of utilizing this in any applications. Earthquake engineering design is more related to the energy, and the energy is related to the force and displacement, all these things. But what I'm trying to say this, like without going to that technically into account, because you have a steel have a very good stress and strain behavior that can be utilized to optimize your structure in a more cost-effective way when there is an earthquake. The second one is like, this is the braced frame, where you have the beam, you have the column, you have the braces. And I think you probably have heard of the braces we need for those for the wind loading. Similarly, it can be used for the earthquake loading also. Now, these braces, I'm just coming to one of the point. People say that like your section, steel section is a hollow section, or very, very small sections which can buckle. But this buckling, which is probably can be seen from here, that is again utilized to increase your capacity to resist the earthquake loading. The third one is similar to the reinforced concrete shear wall. We have the steel plate shear wall. It's exactly the same concept where the beams and columns. Now I think most of you know that in India the RC shear wall is very, very common. In concrete, in the steel, the shear, the thin plates can be utilized as a shear wall. And the best thing is you can see like, it gives you a lot of information. Like one of the tests we did at IIT Delhi, you can find out like these are the columns, even the very high earthquake magnitude. There is very, very minor damage to your columns. The another concept is called the steel truss moment frame, where you don't have the beams. So essentially your slabs are actually supported by some truss kind of a system. And you design those truss, like you can see this structure. There is no beam. Beam is replaced by an open girder system. It's a truss system. But the truss is designed in such a way that like whatever the earthquake force is, expected at the design level or the maximum expected level, that truss should be good enough to release that input loading. So this is the best part is it also allow you, like sometimes you have the duct for the passing of the duct, you have to drill or cut the hole in the beams. You don't have to do that. That provide you that kind of flexibility. It's called the STMF system. The another system is, again, this is a new, completely new system. The advantage of this system is you can have literally a column-free structure. Column-free structure means like you have a slab here, you have a slab here. There is no beam. The only thing is there is a truss which is connecting from this slab to this slab. So it's essentially transfer from this slab to this. The load is transferred from this slab to this slab, this slab to this slab. And in between this, there is no columns. It can be utilized. One of the example in the Chicago is where around 120 meter is the column to column distance people use without intermediate columns. One of the best example, and it's a new technique probably like it's new to India, but in most of the countries people are used, is called the buckling resistant braces. This is one of the systems is very, very effective in the earthquake resistance design. And what it actually does is a very simple system. You have the beam and column, and in place of the beam and the conventional brace, you have a new system. It's called the buckling resistant brace. The idea is like, if you have I can show you some pictures. You have some column here, you have some column, you have some beam here, and these two braces are there. And whenever there is an earthquake, actually they carry that earthquake force, and without any buckling or the failure of the system. Okay, and this system is a very very you can say the energy dissipation capacity, and you don't have to replace those damaged members all the times. Some of the tests we did at IIT Delhi actually shows excellent earthquake resistance property. So there are some buildings where people are exploring to utilize this. This is one of the buildings in Taiwan where people use for the residential building. For the school buildings in Taiwan, when many people have used, or many cases people have used the BRBs. So like you have, depending on the demand, you can have one BRB or two BRB at the same location. The second part is the composite construction, where the first part is totally on the steel. The second part is where how we can use the structural steel in the concrete itself. So what we say always, like, our concrete is weak in tension, or the steel is, weak in the buckling or the fire. So if we can combine both of them, probably we can eliminate the limitations of either concrete or the steel. So this is called the concrete filled tube. Like you have the normal steel tubes, you fill it the concrete. And what happens that thin sections which are prone to buckling because of the concrete, actually your buckling is eliminated. At the same time, like if you can actually compare just a simple, just one, instead of like Fe 250 steel, if I use the Fe 350 steel, the strength of the column increased nearly like 2 to 10 times depending on the design. This is called the concrete filled tubes. Your construction is, it can be prefabricated, the most of the things, and the only thing is you have to do at the beam column joints, you have to do a casting there. The another concept is like I can use the steel inside the concrete. The previous one was the concrete inside the steel. The second one is steel inside the concrete. What happens like in, when you have very highly reinforced steel, so it may have the congestion. At the same time, this steel is actually confined by the concrete. That means you are effectively increasing the concrete, the steel strength. And this is one of the good technique which can be particularly used for your stilt building, where your soft story building, where your stiffness and strength requirement are the soft story is very significantly high. So either you use your significantly high dimension of the columns, or you can combine the steel and the concrete to utilize their stiffness and strength. Again, as far as the earthquake resistance is concerned, like we tested around 10 to 12 specimens. It's very good. So if you try, think of how to connect those, probably like this part which is inside this joint It can be actually fabricated in the shop or and then at the site, you have to just provide the formwork for the concrete casting. In addition to this, we know that there's a cold form steel people use. The cold form steel, mostly people use for the prefabricated structures. But now with utilizing the techniques, the design provisions, even one can replace the entire concrete column by the cold form steel. That means it's not for just facades or some kind of the architectural requirement. The cold form steel can be used for the primary beams and columns. So some examples are utilizing as a built-up members. As I said, like the steel can be utilized for the retrofitting applications in India, particularly the retrofitting area is one of the major area where many buildings are actually seismically deficient. I think the best or the faster construction can be utilizing the steel in any way, like the braces or the steel plate shear wall, or by using the damping or by using the BRB. This is one of the examples where we use the BRB for the a sub-story building retrofitting. I think this is my last slide. This is one application which is already in place. Most of you have heard of the earthquake. It is called 2011 Christchurch earthquake. And after that, the Christchurch or Canterbury area, actually they come up with how to entirely retrofit all the buildings. Out of the retrofitting strategies, they decided, they explore all these things, because remember, like in New Zealand, most of the buildings are insured. So many buildings which are earlier in the concrete buildings, they are completely replaced by steel structures. So one building, I'm just showing this. This is one direction they use the BRB, in the other direction they use the STMF, because this insurance company is essentially the liability, and that means you have to say that, okay, what is your damage levels, and that you can only confidently say when you know the material modeling of the system. That means if there is the same earthquake actually strikes after 5 years, my building, how much damage, whether that damage is acceptable to me or not. So most of the retrofitting or the new buildings is completely use the steel elements, many things which I actually discussed in this presentation. So it has a good potential, not only for the pure new construction, it can be for the retrofitting of the old structures, or utilizing the new, innovative ideas in the structural design. I think that is the last slide. Thank you so much.